Web engines have evolved into these sophisticated virtual machines, and I got told when I got invited to speak here that we were going to be talking about virtual machines a lot. So if you've seen a Servo talk before, this one's going to be a little bit different because we're going to go at it from sort of that angle. So millions of developers build for the web, and all of that code runs pretty much on everything that we have. And people have been trying to use web technology to build other things than web pages for pretty much since there was a web. But up to now, it really hasn't been all that great. So I think we can do a lot to make this a lot better. So one, Space Jam is forever. So describing why the web is horrible is like describing why it's horrible to drown in an ocean composed of pufferfish pregnant with Freddy Kruegers. For those of you like me that sometimes hate the web, like this probably rings true, and the web certainly has its rough edges, but it also has a lot of great things, and lots of other things have rough edges too. So you can probably replace the web here with Java, Android, Windows, pretty much anything you want, and it's still just as funny. The web's 20 years old, but the Windows API, Objective-C, they're actually 10 years older. The only thing that's really newer than this is Android, and that has its own share of problems. So, everything, like all models are wrong, all these things are terrible. But the web also has real strengths. So the web runs everywhere, on every platform. You can design for desktops, on Windows, on Mac OS, on Linux. You can put it on your mobile devices. It runs on Raspberry Pi sometimes, if you're willing to be patient, and things like that. And this is pretty unique. So to give you an example, I don't know if any of you remember the Chandler project, which was this project by Mitch Kapoor to, sort of do a new version of his Lotus agenda from way back, even before my time. There was a nice book about it called Dreaming in Code. And in that book, they're talking about this project totally failed. And so this is a project about a doomed software project that is highly recommended. And in that project, they had this one bug, which was when you resized the window that they were working on, it would flicker. And it took them over 2 years to fix this bug. Part of the reason for that was on every platform, it was a different bug. So the web certainly has cross-platform issues, but they tend to be relatively minor compared to that kind of thing. I don't know if anybody here's programmed in WX widgets, but that's what they were using in Chandler. So not only that, but you get a lot more platforms sort of out of the box than you get with WX widgets or one of these other sort of cross-platform libraries. And another nice thing about the web is it has all this great stuff in it. And most of that stuff, even the new stuff, works on all of the platforms, like WebRTC, for example. Now, on the web, code is nearly immortal. This is Space Jam, which came out in 1996, which is over 20 years ago. And it still works today. And I have to say, this is probably the biggest ROI that internet advertising is ever going to get. So not only are web browsers compatible with content that content from the last 2 decades, but new content will often use features progressively. So if you don't have support for this newest API, they'll use a slightly inferior way to do it, and the app will still work. So it's generally sort of forwards compatible as well. And they'll fall back to alternatives. You can be pretty confident when you write code for the web that it's going to keep working pretty much indefinitely. Windows is probably the other platform with as much attention to compatibility as the web, but even it doesn't do as good of a job here, mostly because binaries aren't portable. Websites are basically robust even to changes in system architecture. The worst thing that pretty much can happen to your web stuff is if your backend service stops working, but this is actually no worse than everything else, which uses backend services. And the web is easy to learn, so pretty much anyone can do it. All it takes is a text editor and a browser. Any computer you get already has those things, so everyone has the tools in hand. The web also was designed helpfully with view source there, and browsers have developed these amazing inspector tools, so you can go figure out how web pages are constructed, how they do their fancy animations and all that kind of thing. So that's really nice. And all of these features of the web, they start to accumulate and add up to make something really compelling that developers want to build for. And they certainly have. So this is the Stack Overflow survey for popular programming languages, and it shows JavaScript is the most popular programming language. But sort of more interesting here is like 8 or 9 of these languages on this list are web-related in some way. It's probably true that if you're a developer, you're likely a web developer, or have been in the past, or will be. Sorry. And for more than a decade, actually, it's even longer than I thought, because I realized earlier that this happened even earlier. I was going to say Firefox 1.0 came out in 2002, and it was constructed trying to use web technology as much as possible. As we used Zool, and we made all this stuff so that we could build the browser out of sort of web-like technologies. But I was wrong. It's actually happened 5 years earlier, if anybody remembers Active Desktop with Windows, which launched in 1997. So people have been trying to do things that aren't the web browser with web technology for a long time. Thunderbird came out in 2004. Songbird in 2006. These all sort of use the same Firefox-type technology to do this. And back then, like, the web platform wasn't as nice as it is now, or some would say better. And we didn't really have the tools to do these kinds of things, so we had to make some things that were sort of a little different, but it was still pretty close to the web. Web developers never give up, though. They keep trying to build these things. So they try to build mobile apps out of the web stuff, try to build desktop apps out of web stuff, and sort of the ultimate conceit of the web developer is to like try to make your own operating system out of web stuff. And there's certainly a mixture of success and failure in all of these things, especially now that I added Active Desktop to the list. But things keep improving. So I think Node.js is a really good example of what happens when you make some new area available to all of the huge amounts of developers that are familiar with web technology. Giving access to server-side code with the same sort of tech stack that they're already familiar with has been a huge success. There's been tons of mentions of Node at this conference. There are whole Node conferences. It's pretty amazing. So far, I mostly talked about the benefits of the web, but there are some problems, and one of them is performance. So we are not tall enough. So if we go back a few years to the launch of Netscape 1, this was 1994, so 2 years before Space Jam, because that's my frame of reference now. And if you were using Netscape 1 and you had like the latest, nicest computer, you probably had a Pentium. And back then, processors mostly ran one instruction at a time, but the Pentium was better. Like here, you have the first superscalar Intel processor. It can sometimes run multiple instructions at once, although from the same instruction stream. It had 3 million transistors in it, which at the time was considered a lot. And in 2002, Firefox was released, and you might have had a Pentium 4. And the Pentium 4 was the first Intel processor with hyper-threading technology, which pretended to be multiple CPUs by keeping separate execution state but sharing the execution units. And now we're up to 55 million transistors. And in 2008, we have the first Core i7, which is now fully multi-core. We added a lot of transistors here. There's 730 million in this, so we basically did a 10x thing here. But you can see they're divided up among all these cores. And here we start to have a problem, because browsers are single-threaded. And they're still mostly single-threaded even today. So sure, we can sort of split the browser up into multiple processes and be able to multitask better by running one process on one core, another process on another core. But this works pretty well on the desktop, but on mobile this isn't very good because you're only ever interacting with one page at a time, really. You want that page to be fast, not the other things in the background to be fast. And it doesn't have to be this way. If you look at the structure of web pages, they seem like you could use parallelism to attack this problem somehow. They have these repeated patterns, they have separated areas, they're kind of fractal in that they're made up of these boxes, and those boxes are made up of these boxes. So surely we could throw some parallel algorithms at this and make some progress. And if that was all it is, I think we would have done it by now, but the problem is that parallel programming is really hard. So this is David Barron. He's probably the most experienced engineer we have in Mozilla, and he put this sign up next to his standing desk, and I think it's really appropriate. It's about 100 feet tall right now. It says, "You must be this tall to write multi-threaded code." So this guy, excludes himself from the list of capable programmers here. And it's not that writing multi-threaded code is impossible, but it's just too expensive to be practical. It makes, you get all kinds of new bugs with data races and these things. It makes the debugging a lot harder than it was before. And on top of all that, you still have to come up with these fancy parallel algorithms. You can't just do, the normal, tell the computer to do X and Y and Z in a certain order and get the job done. So we had an idea. We thought, maybe the problem here is C++. So we decided we'll rewrite C++ from scratch, and we'll take that and we'll rewrite a browser from scratch. And maybe we'll actually end up with something that can make writing parallel code practical. The language we ended up creating is called Rust, and there have already been a lot of talks on it here, mentioning it here already, so I assume everyone pretty much knows what it is by now, but it's a new systems programming language. And with this, we started to write Servo. Rust has all these nice properties. It's fast, it's reliable, it's productive, the little triforce of things there. But it also has a lot of things that are nice for helping write Servo. So a good example of the safety properties of Rust is this web audio API. Now, web audio just allows you to sort of manipulate audio samples in JavaScript. There's nothing tricky about it. There's no security implications. The NSA can't listen to your phone conversations by you making clumsy mistakes in your web audio code in JavaScript, except that in this implementation of this sort of standard web API, there were 34 security critical bugs, and just FYI, those are the ones that will own your machine. All of them were array out of bounds or use after free type violations, and all of them would have been prevented by the Rust compiler had this component been written in Rust in the first place. Aside from these sort of advantages, Rust also gives you more fault isolation in general than C and C++ because it can trap errors at thread boundaries instead of just crashing whole processes. And one nice thing that happened is Rust is memory safe, it's data race free, and it turns out that the properties that help make it data race free also were the properties you need to make multi-threaded programming awesome. So that was useful. I'm not sure everyone expected that at the beginning, but it certainly turned out that way. So maybe we'll take credit for it anyway. So we started writing Servo, and a lot of people want to know, why is Servo fast? And Servo's fast because we try to take every single piece of the browser and make it parallel. We've done parallel layout, we've done parallel styling, we have split up the way the browser works into lots of separate threads that communicate with each other, so that's parallel. We call that the Constellation. We have taken rendering and sent it to the GPU where dozens and dozens of little instruction cores can make things really fast. And this has been really successful so far. So I'll show you a little bit of details about some of these. So let's look at parallel layout. So this is a visualization of a page that has been laid out on multiple cores. What we did is we took the normal Servo display list and we annotated it so that the borders of every element that we laid out get colored by which processor did the calculation. And so you can see we're really good at laying out Reddit with lots of the CPUs. This page parallelizes really nicely, and a lot of the web parallelizes really nicely, but there are some web features that make it not parallelize so nicely, like floats. The next thing I want to talk about is the Constellation, and to describe that, we sort of have to look at a sort of simplified view of how browsers work. So this is like how they worked a long time ago, which is that you had all these tabs, and they went into this single-threaded engine, and that single-threaded engine would then paint stuff to the screen. And then we got, and this is how basically it worked until Chrome. And then we got Chrome, we got multi-process, so now we can split these tabs up over some number of processes, but otherwise those processes are still single-threaded. This is still true today in Firefox and Chrome. And this, of course, has some nice properties, like, if something's going on page A, then the browser Chrome is still fast. If page B crashes, then it takes down page A, but not the browser Chrome. So this is definitely better, but we can do even better. So the first thing we did is we split up all of the things that would block script execution into their own threads. So you have a script thread, you have a layout thread. It's not pictured here, but when you get to the rendering part, that's on its thread. There's things that have helper threads. So as much as possible, we've gotten stuff off of the main thread. And this means that we execute some script, you make some changes to the DOM, we can start laying them out, and then we can go back to running script while layout is finishing. Layout finishes, it sends a message over to the renderer can render things, script is still running, layout is still running, everybody's having a party. And using the whole CPU, hopefully. And these pipelines, that we call them, can be combined. They can contain other pipelines, for instance, for iframes. And the tree of these pipelines gets managed by this thing we call the Constellation. And aside from being able to do more things at once and not block script execution, Rust, with its sort of trapping errors on thread boundaries, allows us to do things like if a layout thread crashes, it doesn't affect script at all. The user can't actually inspect any of the state of the layout, so we can just restart it. You'll never even know. And same with the renderer or the script thread itself, although if certain ones of these crashes, it will be noticeable. It just won't affect very much. So this has some useful properties, especially around iframes. So if you have cross-domain iframes, they can't talk to each other in JavaScript, and so you can give them both their own script threads, and they can run completely side by side in parallel. And this is really interesting when you get to advertising, because all ads on the internet, pretty much, are in cross-domain iframes. And this means that in Servo, every ad that you see gets run totally in a separate thread, and it can't interrupt your interaction with the page that you're on. So it can do all kinds of crazy things, and sure, that will consume your CPU resources, but the rest of your browser stays responsive, and you barely even notice. So remember this. This is where we were in 2008, 730 million transistors. And the problem here is the hardware people kept getting better and better ideas, and then we ended up here last year. So now we added 1 billion transistors to what we had, so now we have about 1.75 billion total. And you don't have to stare at this too hard to figure out what they did with all of those new transistors. They did not give them all to the CPU cores. They gave us this big GPU over here. Since the whole goal here is to make things fast, to use the whole computer, now we have to come up with something to do for these 600 million transistors or whatever. So we created WebRender, and the idea is we'll take all of the painting and rasterization that the browser has to do, and we'll move that all over to the GPU. So the key ideas here are, we wanted to change the way that the rendering algorithm was done from sort of an immediate mode API, draw this, set this state, draw that, set that state, a very imperative paradigm, to this retained mode. And this gives the GPU and the drawing algorithms all the information that it needs to switch things around, to optimize it, exactly how the things should be batched together, to reduce overhead and things like that. And we sort of base the things that it can draw on the actual CSS concepts. And there aren't that many of them. So for example, in Firefox today, there's probably 90-something things in the display list. So 90 different things that Firefox knows how to draw. So they're fairly low-level things. In Servo, that's the complete list right now. It's not very many. It's really 6 or 7 things, except for a couple special cases. The other thing we do is we draw the whole frame of the web page every frame. So we rasterize every pixel every time. And now, that's kind of backwards from what people have generally been doing, because they don't want to draw. They want to draw as little as possible. So when in the case where you're sitting in a text field with your cursor and the cursor's blinking and nothing else is going on, only 12 pixels are changing. And so browsers are optimized to like figure out which 12 pixels are changing and only ever paint those pixels. So rasterizing every pixel, every frame certainly makes that case a little bit slower. But the benefit is that the worst case is now the same speed. So this means that we can now support full screen animations with all kinds of properties, not just opacity and transform, at 60 frames per second or even more frames per second without any trouble. And it turns out that this invalidation that it's doing, figuring out which pixels it should draw or not draw, is relatively expensive operation. And the time that you really don't want to be doing extra work, which when you have to draw all the pixels anyway, you shouldn't be wasting time figuring out that you have to draw all the pixels anyway. So it really punishes you in the wrong cases. And last, if we move stuff to the GPU that used to be on the CPU, well, now we have more time to execute JavaScript, which is pretty great. We don't even have to wait for the JavaScript engine people to make it faster. We can just give them more CPU cycles. So this video was made by the Chrome team. Let's see if I can figure out where the cursor is. Feel free to yell it out if you see it. Oh, there it is. So here we have Chrome Canary at, I think, 9 frames per second. Firefox, WebKit at 5. And Servo's just happy. No problem. And actually, in most of the benchmarks, we do very little work on the GPU. It ends up being like 3 milliseconds, and the CPU prep ends up taking more of the time. So these are all cool things. We're certainly working on a lot more of them. You should be able to start using these yourself in Firefox later this year. We took the CSS styling system that we parallelized in Servo, and we're basically dropping it right into Gecko, replacing their CSS styling system. And I think the current benchmarks on that it's a 10x improvement for styling speed in Gecko. There we go. Problems of many sizes and shapes. So if we want web developers to build more things with web technology, and now we've solved some of the performance problems that maybe were inhibiting them, it probably makes sense to spend some time figuring out what they want to use it for. So of course we have browsers. This is actually a native Cocoa application embedding Servo. So that's one way you could do it. And this is how most browsers are built. We can actually go slightly more meta than that. We can actually build all of the browser Chrome in Servo itself. This is Servo Nightly running with browser HTML. So it's a browser built in the browser. So it's really nice. This is more like this is the way Chrome, I guess, is sort of constructed, and this is the way Firefox is constructed. We also have web views, and these work really well on mobile platforms. Like if you're in a Twitter client, you want to click on a link, and Twitter doesn't really want to kick you out of their application. They want to keep your eyeballs there so they can continue to monetize them. And all of the mobile platforms have pretty good APIs for this, but on desktop, you don't. You pretty much have to go find some third-party library and hope you can get it working. We also have developers building apps. This is VS Code running in Electron, which is a mixture of Blink and Node.js, if you aren't familiar with it. And these are kind of interesting because lots of web features here are not needed. So for example, what's the point of going backwards and forwards in this app? So you don't need any of that. History, navigation, those kinds of things don't have any meaning here. And so it would be nice, or maybe you do want them to have meaning, but it's not the same meaning that a web browser would have, so you'd want to override the behavior. And of course, you can do even bigger things with apps. For instance, this is A-Blast, which is a web VR game using A-Frame. And I've actually played this on the Google Daydream hardware in Servo. It runs really well. And I think it runs on Gear VR as well, like 60 frames per second, no lag. It's pretty nice. But the nice thing here is like A-Frame is a lot easier to use if you want to like experiment with making a VR game than learning Unity or Unreal Engine. And then you can package this up as an app and ship it in the Steam store, for example, which is pretty cool. So you can basically take advantage of the cross-platform distribution mechanism of the web and sort of the ease of the development. And then there's people doing totally crazy things that are really hard to put in a bucket, except if unless that bucket is labeled other. So this is Argonne JS, which is an AR framework. And what it's doing here is it takes the camera input from your phone, and then it layers web pages. So each sort of AR app is a web page with a transparent background that's layered on top of the camera, and then it layers multiple of these things because you might want to have an app that tells you the current directions, but also like your Twitter feed, or I don't know what people are doing with AR these days. But so this is really different than how web browsers work. I mean, I guess the closest approximation would be is if you had all your tabs and then you just made them all transparent so you could see them all at the same time, and the camera. And it has a whole bunch of machine vision stuff so that it can figure out where objects on the, in the display are supposed to be in the camera and stuff like that. So this is using web technology in a pretty unique and sophisticated way. So if you want to build one of these things, this is sort of your list of current options. You have the WebKit API, which allows you to embed WebKit. You have web views, which pretty much only work on mobile. On mobile, you also have Chrome custom tabs, which is kind of a way to do a web view, but in the actual browser. So you still have the same cookie jar and all of that stuff that you would, and you don't have to log in both times, like through the web view and through the actual browser. There's things like Chromium Embedded Framework, which were used to do web views on desktop applications. But that's actually not made by the Chrome team. That's a third-party thing that someone made, and they have to like constantly keep it up to date with the latest version of Chromium, which is probably not very fun. In Servo, we actually support this, except we actually, it's always up to date with Servo. Firefox made Zool Runner a long time ago, and people made some cool stuff with that, but it's officially unsupported. It's kind of one of those Heisen features where sometimes it works and sometimes it doesn't, and depending on Mozilla management, we unsupported or supported. And there's things like Electron, which are relatively recent, which allow you to do apps. So there's a few of these, but it's not quite what we need. So what do we need? The problem is that what we have right now is kind of this Goldilocks solution. It's not too hot or it's not too cold. And what we really need is we need a lower level API that we can use so that people can make these things that they want to make, these apps or whatever, and have the ability to replace parts they need or override functionality or use it in a way that sort of wasn't envisioned. Right now the WebKit API is basically like, load this URL, execute this JavaScript, go forward, go back. It's pretty limited in what you can do, especially if you're trying to do something like Argonne. And then at the same time, we kind of need a higher level API because the web developers out there want to be able to do these things, but right now, you have to know C++ and you have to go download the Chrome source code of a certain version and see if you can get it to link with Ceph, and then see if you can get Ceph linked and figure out where all your DLLs go, and it's kind of a mess, and frankly, most of our team has trouble doing it. So, never stop, never stopping. So let's go back to browser HTML. One thing we learned when we made browser HTML is there are lots of things that a browser needs that aren't necessarily in the web platform themselves, and so they're sort of missing. And some of those things are things that should be in the web platform, and so we should work on adding them. And some things are things that probably should never be in the web platform, but we still need to figure out some way to get them available to this application. So we had this idea to build a runtime based on Servo, so you would be able to build something like browser HTML. And the runtime would execute JavaScript code, but it would also allow you to extend the sort of set of APIs that are there. And it would also provide the Servo engine, so you can manipulate the Servo engine and have everything in one place. And so, for instance, in browser HTML, one of the things you want to do is window management, right? I want to open a second window that's also going to have Servo in it. There's no way to do that in the web platform, really, where you retain control over how the window works. And so we'd have to put something in this added API section to be able to do window management, and then browser.html could use it as it's running. Now, runtimes like Electron already exist. They can do some of this, but the problem is they sort of threw out the web security model, which people at Brave and people at Mozilla found out when they started experimenting with how you could build a browser on top of Electron. Because now you can run arbitrary Node.js APIs on web pages, and that's not really that fun security-wise. So it's a complicated problem to figure out how the runtime should be designed and how all this stuff fits together. And that's pretty much what the whole browser.html team has been doing in the last year since we released the Servo Nightly. The project that they have to do this is called Starlin, and it's just basically getting started right now. And even if we do manage to create this nice runtime, I think we'll get there relatively shortly, we still have another problem, which is that high-level API. So to sort of explain the motivation for that, I'll use this example from Atom. So Atom has this Markdown editing component, Markdown preview component. So while you're typing, it renders the HTML for the Markdown that you're editing, and then shows it on the screen right next to the thing you're editing, which is really nice. Except that, sometimes you're working on a file that's more than like 10 lines long, and so the Markdown generation isn't an instantaneous free thing, and then it actually hangs, and you can't type for a little bit. And then you kind of get frustrated, and then you go back to editing, and then it hangs again. It's really kind of maddening when you start editing reasonably sized files. Like if you want to try this, you can pull up Atom with the Markdown specification, which isn't really all that huge, and you can already see it there as you change things. So this problem is not unfixable. In fact, Visual Studio Code has the same kind of functionality and doesn't have this problem. The problem here is that the most obvious way to build things on Electron leads you to this problem that you end up writing your app as blocking everything, and it becomes unresponsive in these edge cases. It would be nice if you didn't have this problem. So we want to make a new sort of API, a new programming model for designing, for working with this runtime that doesn't have this problem. So we want to make it so that the easiest thing to do, the most obvious way to solve the problem, will leave you with an application that's always responsive. We never want to block things. It's also the case that lots of things that you might want to do in these runtimes are maybe not the best suited for JavaScript, like maybe they're really expensive, like you're multiplying matrices or who knows what. And so you want some way to integrate with Rust, for example. And so the current thinking is that we'll structure apps as collections of services, and these services can communicate with JavaScript streams. The nice thing about this is that it works really well with the async stuff that's already in JavaScript, and it goes very well with the Rust Tokyo API, which is an async library for Rust. And so the idea is you could write this service, and then if it's like the Markdown preview service, if it's taking a long time because it's a service running asynchronously from the main thread, it doesn't matter if it takes a little while. That just means your preview comes up a little late. And then if that does start to cause problems and users complain, you can rewrite that one service in Rust and go about your day. And then we have sort of this crazy idea. We actually call it Magic DOM to optimize the JS bindings into native code. So in Servo, in other browsers, all of the DOM APIs are written in C++, or in our case in Rust. And then when you call one of these JavaScript APIs, it goes across the bridge to the C++ layer and does all of this data marshalling and stuff. A lot of that stuff that those GraalVM folks seem like they're trying to get rid of. We're trying to get rid of it too. We thought this would be a better, more constrained place to experiment with that. So we want to make that really fast, so you don't pay much cost to go across the barrier. So we'd love to have your help. Like I said, this project is just getting started. I know lots of people have ideas about how this should be done, and we can always use more help finding bugs in Servo, fixing bugs in Servo, making it fast. So please come help if you like, and thank you.